Yep, you're live.
And we are live. Hello to anyone out there that's not actually there yet but may enter later or will view us on YouTube. Just some administravia. Olaf and I have been talking, and gathering speakers has been difficult, so we're figuring on canceling the June meeting in light of YAPC and go a bit stronger into July. We're lining up kind of a maker type of talk, Arduino, Raspberry Pi. I've already got a few feelers out there, so if anyone's interested, please fire us a note on the list. Otherwise, here is John Macdonald, High Performance Computing Interface.
Hello, hello. Okay. So I'm going to talk about this high performance computing interface. I'll give a bit of an introduction, describe some of the names that I use within it, how you use it, program access, and so on, status, future, and finishing off. So, if you are running huge programs, they often run on more than one computer. And they can have some parts on one, some parts on another, and so on. These collections of computers have lots of different names. There's clusters, clouds, multiprocessors. And in this talk, I'm just going to call them all a cluster, because that's the one I'm kind of initially focused on. The only reason a program cares about the cluster or cloud or whatever is they want to get their job done. They want programs to run somewhere and results to come back. And most of the time they wouldn't care what kind of cluster it is, except that every cluster has its own interface software. They're all different. So you have to write your program specifically for that cluster. So a cluster, more than anything else, the cluster is defined by the actual interface software. In general, any kind of cluster is a bunch of Linux computers that can run programs and act as a computer. The only thing that's different is the interface, that how you get the thing started, how you test whether they're running, get the results back, job control. So enter HPCI. We're providing yet another cluster interface, but it's an abstract cluster interface. One of the parameters when you create it is specifying what type of actual cluster you're going to run on this time. But the next time you run, you might just put a different value in that parameter and run it on a different kind of cluster. And you can change the parameter either by editing your code or having a command line value that gets put in or whatever. Config files, lots of ways. Now, why would people want to run the same program on different kinds of clusters? Your cluster might be broken and you need to run the program anyhow. You might have a couple of different kinds of clusters in your organization. One that has less ability, but it's cheap. One that has greater ability, but it is expensive. So often you'll do the development and testing on the cheap one and use small-scale programs, test runs. Another big reason is for research or papers that are being published. Often you're getting the research being validated or reproduced, and the lab that's doing the validation or reproduction probably has their own kind of cluster and it's a different interface, but they still want to run the same program. So it's an important reason for being able to move a program. So underneath the hood of HPCI, there's HPCD. Now anybody who's used DBI, DBD may recognize these names or this naming scheme. HPCD, there's a separate driver for every kind of cluster. And its job is to translate the abstract generic functionality into the capabilities and requirements of the particular cluster that is actually present for this run. And HPCD modules are separate packages on CPAN, and you have to load whichever ones you're going to use for the kinds of clusters you need. So the abstract interface has a bunch of components to it. And there they are. We'll go through them all. So there's a group that's the controlling collection for a single thing to be executed, which can have many pieces run on different computers. But it's a single large-scale execution. The pieces can have dependencies for ordering. They may have limitations on scheduling in terms of how many can run at the same time, even if they don't have, one has to go first. There's the whole issues of figuring out when one finishes and keeping track of it and all that kind of stuff, getting statuses, retrying in some cases. So the next basic item is a stage, and that is a logical program to be executed on a computer in the cluster. Now, it might end up under the hood being executed more than once. And the stage itself could run HPCI and control other jobs. But as far as the group program is concerned, you toss it off and it'll run in parallel with other stages. And as well as the command that's actually to be executed, there'll be environmental information. So setting up paths and stuff like that. I'll get into more detail in that in a bit. A run is a single execution of a stage. Usually a stage gets executed once, but we do have some capability for retries. And sometimes it gets run 0 times if a prerequisite failed. There's a logger. It can either be one that the user provides, in which case HPCI interactions with the cluster get logged into the user's log, or it'll create one of its own. It's a log for Perl logger. And resource requirements. This is the most likely thing to be cluster specific and lead to limited ability for porting. Each kind of cluster has its own idea of how you specify what requirements a single execution has in terms of memory and CPU and stuff like that, and how you specify it. And in some cases, there's things that you have to say, and others you don't.
Hello, sorry to interrupt. Could you unmute Dave on Google Hangouts? Thank you.
Someone muted us. Interesting. Okay. Can you hear us okay there?
Yes, thank you.
Huh. That's weird. I wonder who muted us.
Were you hearing the talk until recently?
Missing probably the past 3 or 4 minutes. It's fine.
Yeah. Okay, great. Whoever muted us, don't do it again, please. Think often, there are silence.
Yeah. I don't know if you want to go back to the beginning of your example there.
Well, the last couple of minutes we've actually been wandering back and forth in discussion, so it's hard to figure out what we said. So I think I'll just keep going.
Yeah.
The max concurrent HPCMI, HPCI itself supports it. Even if there are many stages that are capable of being run, this is just a hard limit on how many will run at one time. We'll get into dependencies and other reasons for not running things at the same time as we go on. You can specify the directories based here and grouped here. You can give logging information. And environment passing parameters that will apply to also. And they're described much below. Logging parameters, you can either give it a log, or you can give it either the directory or the file name or both a single parameter. By default, it is groupname.log in the group directory. So no timestamp on this name. It's already in the directory that has a timestamp. So after you've got a group, the next thing is to create a bunch of stage objects. These are the pieces that are to be sent off to other computers. And there's a couple of ways of doing it. The stage method of group is the way of creating a stage object. You must give it a name, and you must, in one way or another, give it a command. Either you can just give it a string as a command, or there's a set command, set Perl command, set Python command, set R command, there's a bunch of command setting ones. They take a list of key value, but it's a list, key value, key value, key value. If the value is a list reference, then it's a list parameter. If it's undef, then it's a flag parameter. If it's a scalar, then it's a keyword value, single parameter. And if it's dash, then it's the remainder of the arguments. And it translates this into the appropriate syntax for lists and flags, number of dashes to use, and so on. You just give the name of the flag.
It looks like it's set for the list hash.
Yeah.
Oh, he's just sneaking.
This is all one list. The first thing is the name of the program, and then the rest is pairs.
Shifting.
So cheating. Yeah, but it's not a hash. It's 2n plus 1 scalars.
It's a 2n plus 1 list.
Yeah. So in this particular case. This would end up being Perl foobar.pl -- verbose equals 1, and then list 1, list 2, list file 1, file 2, file 3. If it had been Python command, then I think this part would be essentially the same. There might be a dash there explicitly. Where it gets different is if it was something like infile equals this, then that would be either in Perl it's dash list file 1 dash list file 2 dash list file 3. In Python it's just dash dash list file 1 file 2 file 3 dash next arg. So it depends on your language. Whether you use this or just write the command out is kind of, I never use the command setting ones myself, and some people know that. It's a convenience if you don't know the language, but if you're writing a program, you probably do. Okay, stage creation has a bunch of parameters. You must have a unique name. A lot of the time when we refer to a stage, we don't use the stage object itself. In fact, if you look back here, I didn't even bother keeping a copy of the stage object. About the only time you use the stage object, or have to, is if you're going to use one of the set commands. You can just paint it directly if that's what you want to do. But you can say my object equals group stage and do stuff. Yep, the group object you use. Yes. Stages are all kept track of inside the group. Okay. So parameters name the command either directly or with one of the command things. There's a dir parameter which sets group dir. There's a hash, resources required, and so that's the key is each underscore memory, s underscore f memory for hard and soft, each underscore time, s underscore time for time limits, memory, it's number and letter, 2 gig, 3 meg, 3 m, 2 gig.
You can specify both the soft and the hard.
Yes. Yep. So the soft limit sends a signal. I think it's user 1. And,
it's a
and
yeah.
Yeah, and after 10 minutes, you're dead.
Cool.
Now the retry resources required, it's another hash, same keys, but each element, instead of having a scalar value, just a string with the value, it has a list ref of potential values. Now, the only thing that I support retry for right now is running out of memory. I don't support it for ton because usually you have a pretty reasonably good idea about how long it's going to take, and if it goes significantly over time, that means you've got a bug in the program that's looping more than you guessed wrong. Yeah. So giving it more time and trying again just means that you'll burn up more stuff. Memory is harder to guess than it is. But what happens is if it fails by running out of memory, it takes a look, how much did we use that time, look through this list, find the first guy in the list that's bigger than that number, run it again.
Presumably after you run, you get some sort of
Yep. Yeah, the log says it failed, it used this much memory, or ran out of memory.
I'm wondering if you might just get that to some idea. Give it 5 minutes and finished okay. 1 minute to 30 seconds.
That's not sure if I always give you time elapsed or not. We'll get into what you get back at termination in a minute. Okay. Failure action. What to do if this stage fails? And there's 3 choices. Ignore it and keep going. Skip execution of anything that depends on this stage, or don't schedule anything after this. Just wait till whatever started, terminates, and flush it all out. And again, there's environment passing parameters. These ones apply only to this stage. We'll get into those in a bit. Like now. So you can specify environment stuff either in the group or the stage. If you give it to the group, it applies to all of them. If you give it to the stage, it applies to that one. If you give it to both, the stage parameters modify what the group parameters set up. If you don't give it to either, then no environment's passed on.
So it'll take, if you provide both group and stage, you have a stage at the top of group.
It sets up a hash for group,
And that applies.
and then when it creates a stage, it says, well, I'll take that as my starting bit. We'll get to the actual parameters in a moment.
The stage capable of 7.
We'll get to that in a moment. Okay, within either group or stage, the parameters you can specify. The source, which by default is %end if you don't have a parent that's already been created. By default in stage, if you've done anything in group, then it'll be the hash that was created in group. Then there are retain or remove, either a list of values to retain or a pattern that is to be retained, and a list of values or pattern to be removed. Normally, if you're using the lists, then you're only going to use retain or remove, not both. At some point, when you do retain, that says keep these and so everything else away. And then if you remove something from that, well, you would just not put it in the list in the first place. But a retain pattern, retain SGE star, and then remove SGE underscore bad flag, something like that. You can use that to clean it up a bit. And the final one is end set. This is an extra hash that just gets dumped in over top of whatever's there. So that's things like forcing the path to be very careful in the path thing, regardless of what your path is to begin with. Now these environment parameters then are put into the script that gets run on the remote system. So the shell script that export, key equals value, a whole bunch of those, command, and in the case of SGE, you do a Q sub. Some can be, I'll go a set of parameters. There's the script to run, and buried in it is the actual command the user asks for. So the cluster interface itself probably does some environment setting. What you get on the other side of the Q sub is already manual somewhere. So what you do here may depend on what kind of cluster it is, and that may limit your portability somewhat. Okay, now once you've got a bunch of stages, you may need to specify dependencies. Often you'll have some number of stages that are creating files that are being used by others, a bunch of analyzing stages, maybe some reporting stages that take some of the analysis and turn it into graphs, and another one that generates some HTML from that. So there's a lot of cases where this guy has to run before any of these. These guys all have to run before that. And when there's a ordering requirement, I call the prereq is the guy that has to go first. The dep is the guy that has to go second within each period. And there is a method addDeps, which can either take prereq or dep or prereqs or deps, and you can have singular or plural mixed and matched. So this guy before these guys before that one, this before that, these before those, whatever, whichever you like. Yeah, for any of those. And it doesn't hurt if you say, all of these before the reporting program, all of these before this guy, all of these ones before the reporting program, this guy before the reporting program. If you happen to say the same dependency twice in different calls, it doesn't care. The restriction is you can't go on a cycle. Because if you do, then this guy depends on that guy, depends on that guy, depends on that guy, depends on himself, the original one, none of them can start. Because everybody has somebody that has to go first within the cycle. Oh. And then the final thing you do with a group is execute it. So group execute. That does all of the executions, doesn't come back until everything that is going to be done has been done. And it returns a status. So the status that comes back is a hash indexed by the stage names, and each of those is a list indexed by the run number, and each of those is a hash, and that final hash always has exit status as one key. Other things according to what the cluster software provides. So in the case of SGE, it's everything that comes back from the queue account. So you get start time and end time and elapsed, and highest memory limit, and it's a whole raft of things. But that again is cluster dependent. There's definite places where moving from one type of cluster to another requires care, or defensive programming to say, well, if I've got this, then I'm going to need this cluster or whatever. Okay, current status. There's two modules which are not yet on CPAN, but they will be in a day or so. HPCI, which includes within it one driver, HPCD-using, which is a uniprocessor. It does a fork to submit the job, and does a wait to collect it. And it supports the timeouts within it. In the SGE, timeouts are supported under the hood by SGE, but HPCI supports timeouts for things that don't have it in the cluster support. But all it can do is kill the local incarnation of the remote job. So there's a limit on how much you can do with a real cluster directly. Now, the uniprocessor version, oh, that should be, yeah, that's right. It's used for testing. When you download, you might not have yet downloaded the cluster module, but HPCI can run through its tests and confirm that it's there. When you download a cluster module, a driver, it'll run through its tests and actually try and use the cluster software. And if it will do some sort of testing to say, do we have access to one of these clusters? And if it doesn't, then it'll just skip the testing. Well, you ask for it anyway. That actually turns out to be necessary in our lab, because the machine that does the nightly build, pulling everything, new version of everything off CPAN and so on, is not on the cluster. So it doesn't have access to SGE. But it still has to be able to download the SGE driver. So you can't have the testing. And there are a couple other modules that run into the same sort of thing. The SGE driver, we've been using it for more than 6 months now. It's gone through a lot of refactoring. It actually started as a bunch of modules that were SGE specific. And then I just turned them inside out and separated them into SGE specific, generic, and most of us encoded with generic, with just a couple of supplements that are there. But we've been continuing to use it for a number of programs all along, and it's fairly well tested and running. And in the future, next big thing is building a community. I don't have access to lots of different kinds of clusters, and so I can't write the drivers for the clusters I don't have. So I'm looking to see lots of people join in. what I'm hoping to have happen at YAPC, especially with people who have access to it. But there'll also be a lot of research labs and so on that we interact with. Really interested in this too.
So you might be able to do you measure for
Yep. Yeah, I expect that to be a fairly popular thing. Now, there will have to be changes to the HPCI interface for the cloud. It definitely would need some sort of authentication, connection, interface parameters. And so that means, it's not just one word you change to run a different cluster. Add the parameters for this. Well, that's not too big a deal. The big thing for clouds is suddenly you're running on a system that doesn't have a shared file system with what you're running here. So there's going to have to be something about bundle this group of files to go and bundle this bunch of files to come back when it's done. And that's not in there at all at the moment. But generally, I want to keep any changes upward compatible. Like adding an authentication parameter for SGE would still work. You only use the extra parameter if it's the system you need it up for. I want to put in a fork, a parameter that is, if the cluster is this, add these parameters. Otherwise, ignore them. So that you can do a bunch of tuning of, here's my program, and get cluster type equals $nVef, cluster type. Yeah. Yeah, or if I'm on AWS, add the authentication parameters, and they have to come out of the config file or something. And some maybe.
Perhaps in the configuration files, it's going to be set up annotators, which person can have their own AWS. Their own billing. It's really interesting.
And I've got a mailing list set up. There hasn't been any mail on it yet. The first group of people outside of Boutros Lab that I've talked to, and the people in the lab all know how to get to me. But that will change very quickly. Sure. Don't have a web page set up. Someday soon. And lots of people in our lab have made use of this in varying degrees.
So these are the people that are making use of it right now?
Just most of them, yes. The first guy there, Paul Boutros, is the head of the lab, Boutros Lab. Down over here in the middle, Chris Lalasing wrote a couple of the modules that I, for SGE management, that I used as my starting point. I don't think there's too many pieces, full lines of code that are for closed race or stuff like that have been unchanged, but any further questions?
Something that strikes me is JCL with extra dimension.
Yeah.
And that was
Yeah.
Aspect
I've long forgotten that.
Huge competition. Is there anything else that tries to move properly to this?
Not that I know of. When I did a search for cluster on CPAN, I found all kinds of things. Cluster is a nice generic word that is used for clusters and graphs and all kinds of stuff. But nothing seemed to be as in computer cluster management.
Also, because I know there's other things that can follow clusters. Has talked about these
I'd have to see what they are and what they do. I have no objections to that. nothing being displayed. Basically, the log is the text file.
Oh, this?
It's a PDF.
It's a PDF. It was written in text.
It's nice to say.
Yeah, well, part of that is by choosing not to do some things that I really wanted to, because trying to figure out how to convince tech not to treat some of these characters as magic, but just use them as they are, damn it! It's, I didn't want to spend the hours figuring out to do something about it. But, yeah, the general layout is
Diagram showing the.
okay.
Questions for
Hello?
that?
May I ask a question?
Sure.
All right. Do you need a batch job runner on each of the systems in the cluster?
That depends upon the cluster interface software. The cluster we have in the lab is SGE. So all that the driver does is it calls the QSub program, and the IT department manages the cluster and how the QSub program translates into queues of jobs and chooses a processor and runs it and tells the original program when it's done. So I'm not managing any of that.
Okay. So if you want to go to cloud, basically you need those machines already managed, right?
Yeah.
Yeah. Well, that's how it stands at the moment, anyhow.
Okay. So there's like no provisioning support. Basically, stuff needs to be up.
Yeah.
Yeah, it's Abram. Sorry.
Get on that, man.
Patch is welcome.
Yeah.
So is there like a good distribution that one could use in the cloud to use this easily?
I haven't done anything in the cloud yet. That's what I'm hoping to get to as my next major project.
Okay.
I'll probably go to AWS. I have to talk with my boss, and it's not going to happen until July that I even start on that. I'm busy getting ready for YAPC right now.
Oh, cool. Well, thank you for answering my questions.
No problem. Anybody else online with questions?
Inflation. It's much more efficient. They need to basically they need to actually inflation.
It's like GCC,
Because first of that
front end and back end.
we've never interacted with databases with PHP.
Thank you.
I
Circle
think
strikes.
to be avoided. Everything is thrown into the model. In fact, there are two models. The model one's fine. But that's it.
Okay. Thank you, John. All right.
Somebody who is yes, you would be up down the street. I need the cloud, I need the cloud, I'm gonna write the modules. Yeah. Great.
All right.
Well, there are half a dozen different kinds of things that using it as start doing alone. The rest of the half dozen is still not yet supported.
All right. Next up is Richard Farr talking to us about the RAF consensus algorithm. Hey, Richard.
All right. All right, well, I'll get started. So my talk would be the raft consensus algorithm. So first of all, I guess before we get into what it is, why? So you need a state machine with the following properties. It's replicated because you want to avoid data loss, highly available, consistent, dynamic, simple, relatively speaking, and performant, obviously. So some things, for instance, that you could use this for: audit logging, so durable and secure from host compromise; invented command sourcing, so persistent record of state changes in your program; published serialization points, where you want to hub sub and you want to guarantee a certain order. Basically, consistent distributed systems. You can run multiple instances in parallel and have seamless failover. So kind of the history on this is that the work began in the mid-1980s. Opie and Liskov published view-stamped replication in 1988, and shortly thereafter, it was quickly followed by the work of Leslie Lamport, who derived the Paxos consensus algorithms, named after a fictitious legislative consensus system. And Paxos had an elegant formalism, but was relatively complex and difficult to grasp. So in 2013, Ungaro and Oosterhout published the raft protocol, and their main purpose of this was to aim to be simpler. So an overview of raft. Think of it basically as a replicated state machine cluster. You can use cloud, you can use different terms, but I'll just use cluster in this thing. So you have clients, one or more, who publish append-only command logs to the cluster. One node is considered the leader, while all the others are followers. The leader has the complete responsibility for managing the replicated log, and they also determine when a log should be considered committed. And at that point, when it's committed, it updates its own internal state, it executes the command essentially, and the follower state machines as well get executed. And clients only talk to the leader, so they don't talk to followers at all. This is kind of just a basic overview of it. You have your clients over here. They talk to some kind of generic consensus module on the server. This manages the replicated log. So in this case, this is just some basic commands of X, change X to 3, change Y to 1, etc. And this is the actual state you will get in the actual program. This is basically application space, specific to whatever program you're running. So just a quick note that Raft does not solve the Byzantine generals problem. So that's where, if you have a certain number of nodes that are malicious, it basically requires the cooperation of all nodes to properly function. But generally, that's not a problem for most clusters. So there's basically 3 sub-problems that Raft tries to solve in a high level. So there's the leader election process. So whenever a leader fails, a new leader must be chosen. There's also the actual log replication itself. So the leader accepting log entries, replicating them across the cluster. And finally, the most important one, safety. Basically ensuring that if any node has committed a particular log, that no other node may apply a different command. Basically, just guaranteeing that the state between all of them is consistent and that there's no weirdness that happens with your data consistency. So a Raft cluster is basically requires a majority of nodes to be functioning. So, for example, if you had 5 nodes, basically 2 can fail and the system can still function. Raft supports adding or reducing the number of nodes dynamically, so that's pretty nice. It allows you to do maintenance and load sizing as needed without having to take the whole cluster offline. So a Raft node is basically can be in 3 states. It's either a leader, a follower, or a candidate. So followers are passive, and they only respond to requests from leaders or other candidates. If a client attempts to contact a follower, it redirects them to the leader. So this is just a way, this is basically the only thing that followers will interact with the client, is to redirect them to the leader. Raft assumes that leader failure is relatively rare, as the system only makes progress under stable leadership. So Raft divides up the leaders into terms, elegantly enough. So the time is divided into terms of arbitrary length. Terms are numbered and are continuous and strictly monotonic. Each term begins with an election in which one or more candidate nodes vie to become leader. And in the case of a split vote, that term will just end immediately with no winners, and a new election for a new term will begin.
Okay, so you said candidate nodes.
Yep, nodes. Yep.
You had three kinds of nodes. You had
So there's followers.
leaders, followers, and candidates.
Right. So followers are not involved in the election at all, other than as voters. Candidates are running for election, and leaders may or may not be dead at this point.
Oh, so candidates are also followers? Then?
Well, they are followers that choose to become candidates. They can switch things. We'll see that in a second. So just a kind of example of a few different terms. So you have your election here, normal operation, then let's say that leader for whatever reason died, another term starts, another election. In this case, we had no emerging leader. There was a split vote, so that term is just discarded, and we need to start another election for term 4. Pretty straightforward. So the actual communication protocol that's used is there's basically only 2 remote procedure calls in Raft: the append log and request vote methods. So append logs are issued by the leader to each follower to ask them to update their logs and with the attached log list. So they basically include along with that a list of entries to append to their logs. It can also be used and is used with empty list as basically a heartbeat. Request votes are issued by candidates to each follower, or to actually really everybody, when an election begins. And generally speaking, all these calls are issued in parallel and are retried indefinitely if a response is not received in a timely manner. So now we'll go through the leader election process. So all nodes begin life as followers. So when you first start up your Raft cluster, everyone is a follower. They remain followers as long as they receive valid RPCs from either leaders or candidates. So if they hear from leaders or they hear from candidates, they will remain followers. If a follower doesn't hear from others for a period of time, and this is defined as the election timeout, it's just configurable, they assume that the leader is dead. At this point, the follower increments its term number, switches to candidate state, votes for itself, and issues request votes to all the other nodes, saying, hey, vote for me. And the candidate will remain in the state until either it wins the election, another node establishes itself as leader, or a period of time goes by with no winner. So this is basically the state diagram of the various transitions. So you start out as a follower, and let's say there was a timeout, you start an election, so you'll become a candidate. And let's say you received a majority of votes, everyone voted for you, you become leader at that point. On the other hand, if you were a candidate and it timed out, you restart being a candidate. And at the other hand, if let's say you discovered that there's a new term or a new leader, you would go from candidate status back to follower. And also leaders can go back to followers if they discover that there is another leader out there that knows more than them. We'll talk about that later. So winning the election is one possible outcome. So when a node receives a request vote, so this is like, let's say, a follower. So it's receiving the request vote. So it's being asked to vote. It votes on a first-come, first-served basis for that candidate, for that particular term. So it only votes once per candidate per term. If a candidate receives a majority of votes, then it considers itself to be leader, and it issues heartbeats to establish its authority with the other nodes. Remember, all the other nodes are potentially not hearing anything from the leader, so as soon as it issues these heartbeats, it's now going to be considered to be tribes.
Heartbeats, you said there were 2 calls.
Mm-hmm. Right. It's the same as the append log. It's just that the log list is empty. So it's an empty array. So just like append, right? There's some other checks that happen with an append log, and this is where it's useful. But yeah, it's used as a heartbeat to establish your authority and to maintain contact. So essentially, by allowing only one vote per term and requiring majority rule, the system guarantees that there is only one leader at a time, which is important. So another outcome is losing the election. So a candidate starts an election, and while the candidate is waiting for votes to come back, it could receive itself an append log RPC from another node. And if the term number of the other node, so when you send this RPC, you include what you believe to be the latest term number, your view of the world. If the term number of the other node is at least as large as the candidate's term, basically, then it goes back to a follower state. Basically, it accepts the authority of the other node. However, if it's smaller, then the candidate rejects their purported authority and continues waiting for votes. So this could happen if a leader was trying to establish authority, but it's out of date, it's in the past, and so you say, no, you're not leader, you don't know enough. So, and then the final outcome could be also a split vote. And this is possible where no one wins. When let's say you only had 4 nodes in the system, and it was a split vote 2-2. There's no requirement, for instance, that you have to have an odd number of nodes in the system. So after a certain time, the candidate will basically give up and restart another election. And there's a timeout that will be randomly selected to minimize the chances of repeated election cycles, which would be very inefficient. That's classic.
I'm surprised you have that in there, Richard. I'm not sure you knew about that.
So this is basically the basis of leader elections. There's also some additional constraints on who can win an election. We'll discuss that later when we get more to the safety properties. But that's the basics of the election. So now we'll go into how logs actually get replicated once there's a leader. So the leader will receive a client request and will contain some command to be executed upon the state machine. And the leader appends first to its own log internally, and then issues these append log RPCs in parallel to all the other nodes. So basically says, hey, all these other guys, look at this log. And once a majority of the nodes respond saying that they've persisted it to themselves, then the leader will consider it to be committed. And at that point, it actually executes the command on its state machine. And at that point, it actually returns the result of that command to the client. So from the client's perspective, this is just like a normal method call.
So majority is literally,
It's like you have to have at least, it has to be half plus 1.
Now, earlier we were talking about if there were 5 nodes and 2 that were dead, so you only have 3. So how does the system know that there are 2 nodes are dead, so there are actually 3 nodes? So once I hear from 2, then that's a majority.
Well, in that case, if there was 3, it would hear from another one, and it has it itself, so that would be considered a majority. Because there's itself plus another node have it. So with 3, it would still work, right? It's not a majority of the other nodes; it's a majority of all nodes.
Originally, there were 5 nodes.
Yes, and now there's 3.
Now there's 3.
Yeah, one of them's the leader.
But he's expecting to hear from 5 all
Yes,
2
you're
are
right.
now dead.
Yes, you're right.
So then what happens?
So he still hears from the majority. He hears from there's 3 nodes functioning still. 2 are dead. Right? So 3 is the majority of 5. So that would still function. So the majority includes the leader because it also has its own copy, right? So at that point in time, if the leader has it and then the 2 other ones have it, and then at that point that's considered to be a majority of 5 have it. So it would consider that to be. That's if another node failed, then yes, then the system will basically grind to a halt, which is what we want actually in that case.
I understand this is a weird relationship. That's where it is? Okay.
The question is, how does any node know what constitutes majority?
So all the nodes have a configuration that says how many nodes are in the cluster, where they are, and all that. So it could just say, well, I know that there are 5 nodes in this cluster, and I've heard back from 2 others, and I haven't, so that's 3. It's just based on the count. Well, the config can change, but they all still have config. Like, so if you do dynamically add more nodes, then those guys will know about it too. Like, one of the prerequisites is all the nodes have to know the server or the cluster configuration. Have to know how many nodes there are.
Right, so if you throw in another 10 nodes, you have to figure out.
Yes.
And now we're 13.
The problem is if something dies, presumably last act isn't to say exclude me from the list.
Yep.
So
it just dies. It goes away.
Yeah. So then everything still thinks that there are that many.
But it has to know that it has that many, otherwise it can't. It won't know at what point consensus becomes impossible. Not when it stops responding, but once you get to that half plus 1, you got 1 less than half of the cluster.
Right.
Then it says, I'm fucked.
Well, it doesn't even say that. It just keeps trying, because it doesn't reach the quorum, and it'll just block at that
Okay.
point. So from the client's perspective, it just nothing ever happens. It just calls out and it's blocked instead, which is correct because at this point the system can't function. It doesn't have enough nodes to guarantee. So yeah, so once the majority responds, then the leader returns the result to the client. So let's say a node does go down. The leader will continually retry append logs against nodes that have failed to respond, even after it has replied to the client. So even after a majority, let's say, hey, it's good, those two nodes, let's say, that had died, it will still try to tell them, because they could come back in the future just to get them caught up again. Followers learn of committed entries, so when the leader commits it, because the leader will include the highest index that it has committed in any future append log RPCs. So let's say it committed it, and then it'll send a heartbeat later, and then that's when those two other nodes say, hey, it's been committed, and then they will apply it to their state machines at that point. So here's kind of just a quick diagram of an idea of the different logs. So here you have your leader's view of the world. So these are the indexes of the logs. These are all the different commands. So you could have all these different followers have basically this view of the system. But in this case, you have 5 nodes. And these 3 here, up to this 5, agree. So this is considered up to here is committed, right? But this here, this 8, is not committed. So 7 is committed, but 8 would not be committed at this point because it hasn't been replicated here. And these guys are, trying to catch up, or they're in the past. And there's a way that they will eventually catch up, which we'll go into. So there's kind of the interesting, this log matching property that is kind of an important part of the system to guarantee consistency. So there's 2 propositions that make this up. So the first proposition is that if 2 entries in different logs have the same index and the same term, then they store the same command. And this follows from the fact that each leader is guaranteed to create at most 1 log entry with the given log index for a given term. So if the term is 3, and that leader is the one that was elected, because we can only have 1 leader, and they issued log index 2, then that's the only 2 in term 3 that would ever be issued. Right? So anybody else who has that, who heard that, would have that version. And as well, logs are never reordered. So the basic, this basically what this is saying is, go back to I'm getting lost in my own place. Yeah. So what was I going to say? Log matching property. So basically, this leader has issued 5. In term 3, there's 5 and X is 0. So anywhere it does exist, it's guaranteed that it will be X equals 0. There's a second proposition, which is that if 2 entries in different logs have the same index and term, like before, then in addition, all the logs previous are also identical. And this is guaranteed by a consistency check that the followers apply when they receive an append log. So leaders, when they send out this append log, they also include the previous term and the log index of the entry that precedes the new entries. So basically, whatever the leader's view of what the most current thing that's up to date at that point in time is before it applies as new entries, it will include that. And so the followers will only apply it to their logs if these match their previous view of the world as well. So once a follower returns success, the leader knows that that follower's log is identical to its own up through to the new entries.
Does it send the entire previous chain, or is it just a caching?
It just sends it's a number, so the previous term is just an integer, and it just would send the previous entry would just be the log index. So it literally just sends 2 hits.
Okay. Oh, okay.
Yeah, so it doesn't need to send any of the previous data. It just needs to say this is the last thing that happened, right? And since and so if the leader's view of the world was the last thing was 4.1, and the follower says, hey, my view is also that the last thing was 4.1, I'll accept these new entries. If on the other hand he has something different, he would say, no, screw you, I'm not accepting. So this is where we'll get into the dealing with inconsistencies part. So let's say leaders crash routinely. It is then of course possible for there to be an inconsistent state when some new leader comes to power. It could be that followers are missing logs that the leader has, they have additional logs, or both. Basically, it's a crapshoot. RAF solves this by forcing all of the followers' logs to be overridden by whatever the leader's logs are. So while in by itself this would not guarantee consistent commit order across the nodes, there's some additional restrictions that Raft adds on who can be elected leader that will actually allow this to work. So this additional election restriction is, so you're a follower, you decide to become a candidate, you're running for election, is that the only candidates who contain all of the committed entries for the previous term can actually become a leader. And the way that Raft enforces this is by having candidates, when they send out their request vote thing, they also include the latest term and the index that they are aware of to the voters, kind of similar to before. So a voter, when they see this, they will reject a candidate whose term is either less than theirs, so this person is stuck in the last term, or if they're in the same term, their log chain is shorter than my log chain, in which case they don't know enough and I reject the vote.
So it's not first come, first served, it's first come, first
With
served.
restrictions. Yes.
Okay.
With restrictions. Yeah.
Do you know it's honest?
The first honest candidate, exactly, yeah. And yeah, so this ensures then that only candidates with all the committed entries can then become. So the mechanism now for overriding logs, so the follower comes to power and he's like, yeah, this guy is screwed. How do I fix that? So the leader maintains essentially internally in its own state this next index property, this piston int, and it indicates which log index it thinks will be sent next to that particular follower. So it's individual to each follower. So when a leader first comes to power, it actually really has no idea. So it just says, okay, I'll assume that it's the whatever index I have plus 1. Right? And so then it starts sending out these append log RPCs. And let's say that it's rejected by a follower because it violates the previous matching principle we talked about because the view of the world is different. At that point, the leader will see that it was rejected, and he decrements the next index and then just tries again. Sends out another append log, but this time with the previous entry included. So the first time, let's say he might have sent out, actually it could have just been a heartbeat that he sent out up here. And if this got rejected, he would then send the previous index, and then if that was rejected, he'd send the previous 2 entries, and so on, until eventually, at some point in the past, the node will accept it. So eventually, the log matching principle will be satisfied, and the followers' logs are truncated and extended with years. Yes, and there's actually, they talk about this in the paper. Yeah, that is an optimization that you can do, but they say that generally in practice, the amount of discontinuity is relatively small, and so I mean you can do it that way. There is the follower could reply back with, "Hey, this is actually my view of the world," and then the leader could just do that the next one. They just think it adds additional complexity, but that is one possible optimization that you can do.
Is that a consistency issue potentially?
No, it's just their view is just that the author's view was that this would be relatively rare, and there'd only be like a few indices that you'd have to go back, and it's generally running on a LAN or something. So their view it wasn't necessary to do this optimization, but you could. There's nothing preventing it.
Basically, by 1 and then the new guy comes in. He's got to go back to 1 and 0.
Potentially, actually, we'll talk about that later. There's actually support for snapshots
Or
as
it's
well.
broken. It was shut down.
Well, yeah.
2 gigs of data to catch up.
2 terabytes of pixels to
One
come
at a
through.
time backwards and then one at a time forwards.
Yeah.
So we'll just quickly now talk about the client's view of the world. So clients, basically, they need to be aware of which servers are in the cluster. So the client has configuration that says these are the 5 nodes, for instance. And on startup, they basically will just randomly pick a node, connect to it. And they will just be redirected eventually to the leader. So either they connect it to a node that was down, in which case they will then pick another random one. And eventually, they'll get to the leader, hopefully. Take me to your leader. And there's a problem, though, that does arise. What if a leader commits a request, so it's updated its state machine, but then it crashes before replying to the client? So the client said, set X to 3, and it did it, but then it crashed. So the client never hears back. So from the client's perspective, nothing happens. So it will try again, causing a double execution on whatever the new meter is. To solve this, each client request has a unique serial number that's attached. And when the client makes a duplicate request, the new leader will recognize this because he has a copy of this unique thing. And at that point, he won't actually do any execution. He'll just return whatever the previous response was.
So by then it'll be the new.
Yeah. Then there's also read-only requests. So a client can make not just a state update, but hey, I just wonder what is the current state of the world. So they make a read-only request to the cluster. A leader who is responding could have potentially stale information if it was unknowingly decoded by someone else. I know that happens all the time, but to solve this on read-only requests, the leader basically has to exchange heartbeats with the majority of the cluster before responding in order to essentially guarantee that it is up to date.
To confirm his lead.
Yeah, basically, he's an honest leader. He steps down on the feet. So we're talking about earlier, configuration changes. I won't go into the super details of it, but basically, it allows the cluster configuration obviously to be altered without having to restart the system. Of course, it's not possible to atomically switch all the servers at once to some new configuration, unless, of course, you want to just reboot them. So there's a two-phase system where the old and new configurations run in parallel. And while in transition, it actually requires a majority from both configurations in order to pass anything. So any time before we were talking about a majority, it now requires a majority from both configurations. Hmm? No, that's just me and Vim typing insert twice. And so what happens is each server hears about this new configuration, it switches over. So eventually the old config will be replaced. The idea is, let's say you had the 5 nodes and you wanted to change it and you wanted to add 2 more. You'd have an old config that would say 5, a new config that would say 7. And at that point, while there's a transition in effect, there'd be a vote from the original 5 as well as a vote from the original 5 plus the 2 new ones that would have to pass. A supermajority, basically, from both of these houses would have to pass. And then at that point, RAF would continue forward. So instead of just requiring a majority from the one config, you require majorities from the 2 separate configurations during the transition period.
Senate and the Congress, but we have no Supreme Court.
Yeah.
And I guess if both of them have to pass, and if they don't both pass, then there's an election.
Mm-hmm. And then the leaders would be selected as well from, I'm trying to remember exactly. There's a mechanism where there's also restrictions on who can become a leader during this weird state. Basically, it's like a minority government or something. Mm-hmm. There's some weird rules that come into effect.
What's the mechanism?
Smith and Wesson beats 4 aces. That's all I remember.
What's the mechanism of configuration?
So it is an additional RPC that is added. So there's the basic RAF, which is those 2, and then there would be another call that you'd say, hey, here's a new configuration. So this adds complexity to the algorithm. These are optional things. You don't necessarily have to have them, but obviously they're nice to have. Then there's the other issue of log compaction. So obviously if you have a long-running system, the logs can grow to be quite large, and that, of course, means you can eventually die and run out of memory. So RAF supports the creation of snapshots that allow you to truncate old logs. Each server independently takes their own snapshot. So the follower, candidate, leader, whoever, at some point they decide, I'm going to take a snapshot now, and that's application specific or independent, and they will take their own snapshot. The only quirk to this is that the leader needs to be able to actually send its own snapshot to followers if they fall too far behind. So let's say you have a follower that died and came up, was down for 2 weeks and came back. At that point, the leader's probably pruned all of those old logs. So it has this snapshot that is newer than, but it doesn't have the knowledge to replay that follower completely. So at that point, it literally just tells the follower, here's a snapshot, and just replace your entire internal state with this snapshot.
Here's the last 2 weeks.
Yeah.
Damn it, man, you're too far back.
Here's what I've done today, but it's not going to necessarily have the follower just come back online. It's not going to have the latest state machine state. So how does it do that?
Well, that's what the snapshot does. So the snapshot includes the state. It's It's actually not. Oh, it's just the state snapshot. Yeah.
Okay, so we take the snapshots and really all it does is the new state at the very end of the snapshot.
So everything that happens before that, all the logs that were previous to that snapshot can be deleted because you don't need them at that point. You just replace the state, and then at that point, the leader can say, okay, and then I have these extra log entries from there, and that will get that person caught up to the present. Yeah. So there's actually a really nice visualization of the RAF protocol at the Secret Lives of Data. So I'll just quickly go through it because we've talked a lot, but images are much more useful. So the basic, you start with a single node, and it's just storing a single value. Let's say this is the state machine, storing X. And you have your client, of course, who wants to send the value to the server. So there you go, update that to 8. This is easy with one node. But let's say we have multiple nodes. So here's a high-level overview. So it's basically, you have your follower, the candidate, or the leader. They all start in follower state. And they all start to, so here's the candidate requesting votes from the 2 other followers. And they say, sure, you can be the leader. So that's the leader election process. So now we say set that to 5. The leader says internally, adds it to its log. It's not committed, but it's just added it to its log. And now it goes out to the other 2 saying set 5. They come back saying, yay, we set 5. And at that point, it's considers it committed, updates its state to 5. It hasn't yet. It will. So first of all, it sends out that to do the heartbeat. Okay, whatever. It was supposed to send it back at that point.
Yeah.
The red button.
Here's the timers. So we're going along and we haven't heard from a leader in a while. Each node has its own randomly selected independent timeout. So eventually node A times out first. It says I'm now a candidate. Votes for itself. Sends out the 2. They hear, so now that they've reset their timers, now that they've heard from a candidate, right, their election timeout timers, and they reply back with the vote saying, yeah, you're good. And at that point, you start sending out these append entries, sometimes with heartbeats if there's no data, other times there will be data. And at this point, the system is, how now has a leader. So it just continues running. And this will continue until until basically the leader dies, or there's a network disconnection, or something happens.
One second. I just want to double check that I heard a ding, and I
didn't
hear. I'm not sure. Just making sure we are not muted. We are not. Yay. Let's go back.
Thank you. So let's say that node A dies, timers start running down, node C wins the race in this case, sends out, says give me become a candidate, and at this point, since there's only 3, but there's a majority, which is the 2, because he votes for himself, he now becomes the leader. And again, he's attempting to talk to node A, even though node A is dead. This is an example of a split vote. Let's say you had 4 nodes, and the interval was very close between the 2 of them. So they send out, and in this case, they each receive 2 votes. At that point, they still haven't received a majority, so they're waiting still. And eventually, that one node D times out, revotes, and a new election, and he's now leader.
What is the difference in those timeouts? What is the range of time? Are we talking?
Right. We're generally talking on the order of milliseconds, 150 to 300 milliseconds. They're configurable. One of the things I guess I should mention as well is you want to make sure that the election timeout, the election timeout is smaller, significantly smaller Then, well, yeah, then your network latency, which then significantly smaller than your mean time to failure. Usually, you want to like an order of magnitude difference. Otherwise, you could have spurious screw-ups. You want your network latency has to be smaller than your election timeout, which has to be smaller than your. Yeah, sorry, I probably transposed.
I'm just trying to pay attention. To make sure.
Thank you for correcting me. So here's an example of the log replication. So it sends a change, sent to the followers. They reply back. That's 5. At this point, yes, he responds back to the client immediately, and then sends the. This is just sending heartbeats to the others, which would then just set them to 5. Then 2.
That's neat to see a visualization.
Well, yeah, this makes it like much more understandable. This is pretty cool. What happens if there's a network partition? So we separate those two. So that bottom half they're happy, kind of, although nothing's really happening because there's not a majority. So then a new election happens up there. We now have 2 leaders running in parallel in different terms. So you have this guy still stuck in term 1, there's term 2 up there. So this is the better leader.
Node B was the original leader.
Yes, he was.
So when the client talks.
So we'll see what happens. So there's another client, let's say, and he tries to talk to this guy, but he can't there's no quorum. There's no majority here, so this is just kind of head at the moment. So that client's attempt to set 3 is not actually doing anything. So node B cannot replicate to since there's no majority, so it just stays uncommitted.
So he's going to fail that.
No, he just keeps going indefinitely. He's just going to keep sitting there. He's going to keep trying to send. He's still trying to send to all these people over there, even though the packets aren't getting through. It's basically the system's hung at this point. I mean, it can't make progress. It's trying, and the client, from this perspective as well, this lower client also isn't, as far as they're concerned, nothing's happening. They will, yes, and then they'll try to find another leader. So, and they might then get the proper leader. So let's see then what happens. So the other one sets the 8, and since it has a majority, that top one is still working. And now let's say the network, partition goes away. So now those packets are all going. He's still trying to set 3 on the other ones. But the thing is that this node B sees that, hey, these guys are all term 2. I was at term 1, so obviously I got to step down. I'm no good anymore. He steps down, and basically these get rolled back. This set 3 never happened.
Never have I seen a system where someone was so easily.
Computers. So that's
so easily persuaded.
They are. And yeah, now our log is consistent. This client obviously will get a timeout or some error, and they'll have to try again.
Because you never got a response back saying, yes, I
set 3.
Set 3.
Yeah. And that's the basic example of Raft. Yeah, let me just go back to here. This has been implemented in most languages. I don't believe there is a Perl version. I was looking on CPAN and I did not find a version for Perl. But I know there's a Python version, Java, C, C++. There's actually quite a few languages. So that's actually something I was thinking of doing, is potentially taking a crack at writing a Perl version of this, since it's missing. And yeah, any questions, concerns, comments, or grievances?
You are no longer the leader.
I willingly stepped down. If only you.
So what are people using this for?
So this would be for distributed systems. Let's say you want to run 2 trade systems in parallel, and they're both or 5, and they're all lockstep. They're being updated. If one dies, you can basically have replicated, consistent state machines.
With identical live trails.
How much data can state machines hold?
It's just a program. You can do whatever. So the state machine is just the application layer. It's whatever your application wants, right? So you write, there'd be a callback saying, hey, here's a command that came in, and your program just interprets that command whatever way it wants. This could just be, for instance, it could just be a log. You're just appending logs. So, like for audit purposes, you want to have relatively quick, distributed audit mechanism. You could just do that. And in this case, the state machine is just literally a list or a file. And then you could have a program that's running to do whatever.
It could be just some application that's multiple machines, and then for the chance we have a system doing what they're doing.
Yeah, like so. For instance, if you were doing like a space shuttle or something, you get 3 different GPS systems. You want to make sure that they all agree. You have them all running in parallel, and then you check that 2 out of the 3 match.
Do you have to monitor all this stuff separately, or query this graph system saying, what is the state of you right now? Do you know who's responding and who's not?
Right. That would be, again, I think implementation specific to the RAF protocol. Like if we have metadata or standard commands to get like for monitoring. Yeah. I mean, well, yeah, you could do a read-only request, which is just what's the state. In other words, there was no change in the state. And then, yeah, but I mean, basically, you can think of it as just like a generic function call. It's just one system that's pretending. It's like multiple systems pretending to be one, with the idea that it's 1 or even 2 or maybe 3, depending on how you can run like 10,000 nodes. Of course, the latency gets higher as you have to get more access.
A lot of network.
Yeah.
And basically, what we do.
True, but I mean, the computation could be very complicated too. It doesn't have to just be. It could be a complete like a stage. Hey, go and do this computation. Back to me. So it's pretty generic in that sense. What the command is basically. So yeah, here's a couple of links.
Kind of like that. I'll be the leader for this command, and be the leader for that.
Yeah,
Do them all at
and I'm
once.
thinking about leaders basically retiring after. Just to give somebody else a chance.
But this doesn't allow any parallel, does it?
No, this is all serial.
No.
One stage at a time.
Yeah,
This
this is for replication basically. And yeah, but the leader, I mean, again, the idea is that leaders shouldn't fail. I mean, it's just a machine running. Ideally, the hardware is not going to die too often.
Mhm.
And so the actual like protocol of all this stuff usually doesn't happen. It's all there.
Well, it's interesting.
HPCI talking to multiple raft implementations.
Yeah. Why not? It's another layer of abstraction, right?
Yes, here's your paddle.
All right, any questions from online there? Okay.
All gone home.
Either we're muted or they're disconnected or there's no questions.
All right. Well, thank you very much, Richard. And thank you all. And that's a wrap for tonight. Oh, wait. Oh, Antonio had a question which I could not see.
In case of a split, how can clients know connect to the new leader?
Oh, well, actually, your little demonstration there kind of showed that.
They connect to
They,
the leader replies.
yeah,
Mhm.
if you connect to the leader, then the leader just responds. If you connect to a follower, the follower just redirects you to the leader.
Mhm.
Right.
Right.
So what I think what he's asking specifically is,
But if you talk to one leader,
we never talk to the leader, well, unless you're a client.
well, yeah, you fire it in, and it got to the split, but eventually,
Whenever, like, in that example, whenever like a follower receives an append RPC with a higher term in its own, it immediately accepts that other person as the leader. So that's how you would solve if there's 2 leaders and then the network partition is field. That's how you solve that they say, hey, that one leader over there, he knows more than my current leader, so he's the leader. The followers are very cultish. They will follow the new trend.
All right. Well, thank you very much, everyone. Signing off. We'll see you later.
See you in July.
Yes. As mentioned before, we're gonna skip the June meeting with YAPC, and we're gonna come back strong in July. We're gonna have kind of a maker-themed meet. Already have a few people interested, so if anyone out there in the maker realm with like Arduino, Raspberry Pi, or some such thing, feel free to fire us a message on the list. And even remote people, we'd be glad to have you on. Anyway, thank you very much. Have a good night.